We're going to look at number 6 and 7 of the past paper that I put onto your work scheme. Number 6.1 asks, which car, if any, experiences the greater magnitude of impulse during the collision? Now you know that impulse is directly related to Newton's third law. So that object A exerts a force on object B, then object B exerts an equal but opposite force on object A. So the answer for 6.1, which experiences the greater magnitude of impulse, it would obviously be that they would experience the same magnitude of impulse because of Newton's third law. But of course, as with all of these questions, we have to justify our answer by referring to relevant physics principles and supplying supporting calculations. So, what do we remember about impulse? Impulse is a change in momentum. So, if we could look at the change in momentum for car A and car B and compare them, we could justify our answer to 6.1. So, let's look at car A. Car A's change in momentum equals its mass, which is 1,500 kilograms. Its final velocity was 6. Its initial velocity was 20, which gives us an answer of minus 21,000 kilograms meters second to the minus 1. Looking at car B, its change in momentum equals 1,000. It had a slightly smaller mass than car A. Its final velocity was also 6 because remember the cars locked together during the collision. But what's important to realize is that car A was traveling in an opposite direction to car B, so we gave car A plus 20, so we must give car B a sign of minus 15 because it's traveling in the opposite direction. So actually that comes to 1,000 times 6 plus 15. So we get plus 21,000 kilograms meters second to the minus 1. So you can clearly see here, and we've proved that the impulse are the same. The only thing that's different, or the magnitude of the impulse is the same. The only thing that is different is the signs. Right, let's look at number 7 now. 7.1 asks, which driver is likely to experience the greater force during the collision? Right, we know that, and again we've got to use relevant physics principles and equations and calculations. We know that F net equals mass times a change in velocity over change in time. Now, if two cars are colliding, the time over which the collision occurs is obviously the same for both of them. And we are also being told that these drivers have the same mass. That's very important. So from this we see, because the drivers have the same mass and the collision took place during the same time period, the driver that experiences the greater net force will experience the greater change in velocity. So F net is directly proportional to change in velocity. We can see it from this equation. So what we need to do is look at driver A and driver B, and we have to look at their change in velocity. So we're told that they're the same mass, so we don't have to worry about the mass, just their change in velocity. Driver A, 6. Obviously the driver is traveling at the same velocity as the car, so minus 20, that's his final velocity, so minus 14 meters second to the minus 1. And then driver B, remember, they locked together during the collision, so again also his final velocity was 6 because he's traveling at the same velocity as the car, but they're traveling in opposite directions, so minus 15, so it comes to plus 21 meters second to the minus 1. So therefore, we can see from this that driver B had the greater change in velocity and therefore experienced the greater net force. then 7.2 asks us, using principle of physics, explain how airbags protect the driver during a collision. Well, we know that F net is directly proportional to 1 over delta t. So we can see that if the collision takes place over a greater time, so in other words, we're increasing the time over which the change in momentum takes place. And because F net is inversely proportional to time, if we increase the time over which the change in momentum occurs, we are decreasing the F net. And because we are decreasing the F net, we have less chance of injury to the driver.